Welcome once again to NANDGAME. We're getting close to the end here, so let's jump right into bit shifts. And we're going to do a left shift. Now, you may recall way back in Network, we actually wrote a left shift in software, which we can do since we built a Turing-complete computer. But obviously, it would be much easier just to build it out in hardware and then add it to the computer, and it can just be added in as a normal instruction. So that's what we're going to do. We're going to do left shift. Shift all bit values one position to the left. The lowest bit in the output is set to 0, and the top bit is discarded. This is equivalent to multiplying. And again, we talked about that when we wrote that algorithm back in the software section. So this is actually pretty easy to do. We have this bit splitter, and we hook our input up to that bit splitter. Then we have a bit bundler, and we just hook up each one of these bits one spot to the left. So 0 goes to 1, 1 goes to 2, 2 goes to 3, and we just do that all the way down the line. And the 0th bit, aka the lowest bit, is always going to be 0 because we're not inputting anything. And the top bit is discarded. You can see this 15th bit on the bottom here is not hooked up to anything at all. So we just hook that directly up to the output, and that should be done. There we go. We didn't even have to use any components. We are just rewiring things a bit. And this is the simplest possible solution. Moving on. Logical right shift. Shift all bit values one position to the right. The highest bit in the output is set to 0. The lowest bit in input is discarded. And because the left shift was like multiplying, the right shift is like dividing. And if you understood the last one, this one should be simple. Instead of shifting everything to the left, we're going to shift everything to the right. So 15 goes to 14, 14 goes to 13, and we just continue that all the way down the line. And you can see again, the highest bit on the output, that's 15 here, is set to 0. Nothing is connected to it. And the lowest bit input is just discarded. We're not hooking up to anything. Of course, we got to connect it to the output. And this is just the opposite of what we did with left shift. Again, no components used, and this is the simplest possible solution. Arithmetic right shift. So we're going to do the same thing. We're going to shift all bit values to the right, but the highest bit should retain its value. The lowest bit is still discarded. And I guess this is the shift we want if we're using signed numbers instead of unsigned numbers. So we're going to grab a splitter and a bundler again. So we're going to do exactly what we did before, just shift everything to the right. And the lowest bit input is still discarded. But since we're using signed numbers, and this 15th bit denotes the sign, instead of it going into 14, we actually want to reroute it into 15. And I think we can just disconnect 14 altogether. Hook that up to the output, and let's try that. Okay, so we still need to hook up the 15th bit here, and there we go. We can see that does work here. If we put in something like FFF0, which is negative 16, we're getting the correct output of negative 8. If we disconnect this, well, it sort of just goes wild and doesn't really work right. So that does actually have to be hooked up. Okay, simplest possible solution again, on to the next level. Barrel shift left. The number of bits to move is indicated by the 4-bit N input. So we built this shift left, which shifts a 16-bit number left by 1. But I think the idea with this barrel shift left is that we can shift a 16-bit binary number over as far to the left as we want. We just use these inputs down here to toggle how far we want to shift it over. And it looks like this is essentially just a binary number. If everything's set to 0, we're not going to shift our X number over at all. If it's set to 1, we want to shift it over 1. If it's 0010, we want to shift it over 2. If it's 0011, we want to shift it over 3, and so on until if it's 1111, then it's shifted over to the left by 15 bits. So let's start with the case where we want to shift it over just once. And it should be pretty simple because we have a shift left 1 right here, and we can bring in a select. So we can say if this is on 0, we want it just to have the X value. We hook that up to D0, and if it's set to 1, we want to shift the X value by 1. So we hook our shift up to the X value and hook that up to D1. And let's hook it up to the output just so we can see what's going on here. I have just the value 1, so all zeros except for 1 all the way on the right here in our X input. And you can see the output when we have our flag right here set to 1, it'll left shift it over by 1. Turn it off, and it doesn't shift it at all. We just have 1 all the way to the right, just like we do in the input. All right, so that's our proof of concept. I think the big question is, how are we going to do this for all these values without just having a ton of different selectors, a ton of different shift left components. Let's get it working for this 1 bit here. So if our input here to shift is 0010, that means we want to shift over to the left 2 times, because this is equivalent to 2 in decimal. 0010 is equivalent to 2 in decimal. So if we want to shift it over twice, we need 2 shifters. And let's for now hook it directly up to X. And again, hook our select to this flag here. Hook up the shift left scenario to D1. It'll go if that flag is on. And our D0 again directly to X, just for now. So let's disconnect this one here and connect up our shift left. So there we go. We can see if it's on, it shifts left by 2. But of course, this situation doesn't work where we have 0011. That should be shifting it left 3 times. So instead of directly hooking these shift left components up to X, let's disconnect that. And let's directly hook it up to the output of our first select 16. And we'll also hook up our D0 to that output as well. And we can see what happens, right? If everything's 0, we're not shifting it over at all at the output. If it's 0010, we are shifting it over by 2. And since we can also activate this first shift left, if we set it to 0011, we should shift it over by 3, which is exactly what we see. All right, I've rearranged things so we have a little more room because I think we are going to need it. And let's look at the next bit we have to hook up. If we turn it on, we have 0100. In decimal, that is 4. So let's grab 4 shift lefts. And we're gonna daisy chain them together just like we did when we only had to shift over twice. We'll disconnect our output because we don't really need that and hook that last select 16 up to input to our 4 shift lefts. Then we need a select 16. And of course the select is gonna go onto this bit right here. That will control whether it comes from D1 or D0. If this bit is 1, we want D1 to come from the 4 left shifts. And if it's off, we want it to come from our select 16. Okay, we'll hook it up to the output just to test it. And we can see that this 1 is left shifted 4 times when we have this flag on. If we also turn this one on, that should be 5. 0110 should be 6. And then if we have 0111, that should shift it over by 7. And it still seems to be working if we have just these other flags on. All right, and I'm making more room because 1000 in decimal, this binary number is 8. So we're gonna need 8 shift lefts. Okay, and we're gonna daisy chain them together just like we did with the previous ones. And that looks okay, I think. It's not too messy. And into our first shift lefter here is gonna be the output from our last select 16, which we can also disconnect from the main output right here. And I'm keep trying to rearrange this just to make it somewhat neat. We're gonna grab another select 16, and we're gonna hook up the selector to this last flag here. When it's on, we wanna come from this series of shift lefts. And when it's off, we want it to come from the previous select 16. All right, and then we can hook that one up right to the output. And like I said, with this flag on, it should shift left 8 times, and it looks like it does. And let's test with all the flags on. It should take this one from our input and shift it all the way over to the other side, and it looks like it does. So this is a lot of components. Maybe there's a simpler solution here, I'm not sure. But this is the one that makes the most sense to me. And more importantly, I think it should just work. So let's try a solution. And there we go, 19 components used. We are not getting the message that this is the simplest possible solution, so maybe there's something more efficient out there. But hopefully this solution at least makes some intuitive sense to everybody. And that's bit shifts completed. And that should set us up for this next section in advanced arithmetics and floating points, but we will worry about that next time. See you then.